let's get started. The Zoom people will tell me they can't hear me as usual, I assume. All right. Okay, so picking up where we were in the class, but just so that maybe to make it ever so slightly more self-contained, I'll kind of redo a little bit of what I did last lecture, sort of set the stage. So basically, well, my sort of short-term goal in the course in this next week maybe is to I want to eventually give a statement of weak cosmic censorship, and then we will and the notion of a naked singularity, which will then be a focus of the course. And one of a very convenient tool in those discussions is something called a Penrose diagram, which is also something used. Oh, there's something in the chat. Yes. I guess that means they can hear me. Something called a Penrose diagram, which is a very convenient way to sort of draw spacetimes on the board so it's a two-dimensional representation, but it includes lots of useful information, often the most important information of the spacetime. And so what I had started in the last lecture was doing this diagram for a Minkowski space. And so I'll just sort of recap. I'll sort of do that over quickly, and then we'll increase our level of generality slowly throughout the lecture today. All right, so we have Minkowski space. And as usual, please, feel totally free to interrupt me, ask questions, et cetera, et cetera. All right, so this metric is on R4 with TXYZ coordinates is just this familiar metric. And I guess I'm not sure, again, I guess the Zoom people can see that. It's hard to tell how big the board is. But, all right, again, let me know if you can't see it. All right, so that's the metric, right? That's the analog of Euclidean space. And the first thing we do, so we already did this before, is for this diagram, we're going to introduce spherical coordinates on to replace the XYZ coordinates. And so we'll write the metric is minus dt squared plus dr squared plus, like just say r squared times this metric on S2, given in the standard way from these spherical coordinates. All right, so like I said, we want to eventually produce a diagram that we draw on the board. So we need there are four dimensions here. So we want to get rid of two of them, given that I've written in this already suggestive of what I'm about to do. The Minkowski space is spherically symmetric. So if you had to get rid of two dimensions, it's very natural to quotient out by the sphere. So we can define a projection map. So maybe I guess I have this. So let's define so I'll have a map pi from my R4M to, and I don't know I forget what notation I used last time. M tilde. All right, so from R4M to Q M tilde. All right, which is just TR theta phi. I'm just dropping the theta phi. So Q will be, the manifold Q is going to be R cross, this is now a manifold will be a manifold, well, with a mild abuse of notations, I'll think of the R equals 0 as being included in that projection. All right, so we have this, and then we have the M tilde, which is the, right, just this. Okay, and like I said before, various sort of causal, I didn't make a precise statement before, and I will continue to not do so, but I'll just say that in general, causal relations sort of down here can be lifted to causal relations, and you can lift the statement up here by pi, and the lift will usually be true. So for example, like if we have P and Q in here, and P is in the causal future of Q, then the set, you lift P. So when you lift, you're putting back the sphere, then the sphere is in the causal future of the lift of this. Okay, so things like that. So of course we got rid of a lot of information by doing the quotient, but nevertheless the causal information of down here still is meaningful that it lives. Right? Questions? Okay. Okay. So then the next stage was, all right, so we have this, we got rid of the sphere, we have this T and the R, but it's still, it's still a non-compact space. And well, I mean, I guess the most pedestrian way to complain about it is, well, we'd like to sort of, draw it, and that's hard that it's not compact, but maybe more sophisticated reasons are we want to, it's convenient to introduce maybe some kind of compactifications of the space-time at infinity to allow us to sort of talk about physical concepts which are occurring at infinity. And anyway, and that requires us to, somehow make things compact. But we want to do this in such a way that it retains useful information. And the key observation, which I mentioned in the last lecture, is that conformal transformations preserve sort of these basic aspects of causality. So let's just review that. So remember, so I guess maybe here's a fact. So if you have some Lorentzian manifold Mg, right, and Lorentzian manifold, like this, for some omega, some map, then, it's kind of we know, so this is a conformal transformation, like in Riemannian geometry, it would, change distances but preserve angles. So the sort of the analog here is that, of course, so if we call this, say, eta, of course, so V is time-like or causal for G if and only if it's time-like or causal. All right, that's of course truly an immediate statement, right? Okay, and so the idea is that we want to, we're fine, kind of, if we're interested in these various causal properties related to causality, it's fine to consider conformal transformations of our metric. And with that in mind, we have the following sort of canonical thing you can do. All right, so the first thing we do is we introduce these null coordinates, which we also did before last time. So let's define V equals T plus R, and U equals T minus R. These are examples of what's called iconal functions. So they're level sets. Level sets of U and V are null curves. All right, these are null curves in this quotient, in the quotient spacetime. When you lift them, you get null cones, you get the spheres. Is this, how high, can I write, how far down can I go here? So this is the limit. I've passed the limit even. But I can't understand what I have more space. Maxime looks skeptical. All right. Okay. We'll just stop here. All right. Okay. Yeah. So we have these guys, and so you can do this little a little computation where it's extremely easy to get off by a factor of 2. But if you believe my notes, which you shouldn't, then the answer, but it will play no role. any important role, that this becomes du dv. It looks weird, but anyway, Maxime looks skeptical. So, all right. So you get so you get this. All right, that's fine. And let's keep in mind. So you have u and v, and let's keep in mind the domain of this. So this should be all u and v. Okay. So at first, you would think you can put these in here, but then but we need remember the original q, which came from doing the spherical coordinates. We have this constraint that r is bigger than or equal to 0. So that here becomes that v minus u is bigger than or equal to 0. Okay, and one of the reasons that it's useful to write the metric in this form is that there's now a very nice way to produce a conformal compactification, which is basically the following. So in fact, if you have any, if you have any 1 + 1 dimensional Lorentzian metric written in some with where the can even have a function here, but we'll see in a second a more general version of this. But you have these du and dv. You can always, what you can do is just consider any diffeomorphism you want, really, from take f from the real numbers to I, some bounded interval. This is just some bounded interval. It doesn't have to be, you could have an F1 and an F2 doing this. Let's take a convention that both of their derivatives are, say, positive everywhere. And the benefit of it, then you can change coordinates. So you can take u tilde equals f of F1 of u, say, and v tilde equals F2 of v. And well, first of all, the range and the u tilde v tilde will manifestly cover a compact set now, right? Because whatever the domain of the original thing was, now it's going to be some subset of this in this product of these bounded intervals. But moreover, I mean, what's nice from this, I mean, of course, the change of variables is not too difficult to compute. Well, just write it like this. We have that, and so you would get that minus du dv equals minus 1 over f1 prime times f2 prime du tilde dv tilde. So what's happened here is, you see, you've written this thing, which was covering this non-compact area. So we could pick any diffeomorphisms we want, and it becomes, okay, there's this factor, that's a conformal, this is just multiplying the whole metric. So this thing is conformal back to flat space again, but now covering, manifestly will cover a bounded region. And so we can easily depict it, right? Okay, and so the canonical choice for this diffeomorphism is, in the Minkowski space, is to do arctangent, just because that's a nice function. So we'll pick, so we'll pick f1 equals f2, I'll say of x equals arctangent of x, and then the interval I in that case is minus pi over 2, pi over 2, right? Okay, so I guess I keep writing here. All right, so with those choices, then so what we get is the following. Yeah, so in this case, of course, so the derivative of arctangent is secant squared, and so what we so we have, or the derivative of tangent, sorry. So I mean, so we want to write we have our du dv in terms of that. So So just following what I had before, we have u equals arctangent of u. All right, so we want to write the du dv in terms of these. So I'm just redoing what I have up there. So this is, of course, u equals tangent of u tilde, and v equals tangent of v tilde. And so what we end up with is that minus du dv equals minus 1 over cosine squared of u tilde, cosine squared of v tilde times this. All right, and the manifold that this metric lives on now corresponds to, well, so now we have u tilde and v tilde. So originally, you could think they could choose them in R2, but now these things, this arctan maps everything to this minus pi over 2 to pi over 2 across, well, say squared. All right, and then we still have the constraint because we needed v minus u to be greater than or equal to 0. Since arctangent, the derivative is positive, so then we still have this. So this is that coordinate chart is the domain. All right, so we good? All good? Yeah. All right, cool. All right, so now we can try to draw this. Yeah, and I guess if you want to okay, what do I mean? I should maybe be a little more precise when I say draw it. So what do I mean by draw this? What I mean is I'm going to reintroduce. So I'm going to pretend that this sort of, we have this relation of the t and the r and u and v from before. So so now I have a u tilde and a v tilde. I can now make a t tilde and an r tilde, and then pretend that those are the time space. So if you make this thing to be 1/2 v tilde plus u tilde, and r tilde to be 1/2 of this, I can then, thinking of this as the t tilde direction, that is r tilde direction, I can draw the domain. And what do I find? So here's then here's the picture of I'm going to draw now this domain here. So what I'm going to get is so we have this line here, which this will correspond to. This is when v tilde equals u tilde, which also corresponds to in the lift when r equals 0. So this is from the center of symmetry. All right, and then basically, if you think about it, we're going to get a triangle. All right, and is this big enough? You can see that? So this is going to be v equals pi over 2, and this will be u equals, I think, minus pi over 2. Okay. All right. Okay, and that's sort of the first approximation is the Penrose diagram. All right, and again, so what's convenient is, sorry. Right, in which maybe let's also say, so I wrote here, this limit here corresponds, this region is inside the space-time, with boundary and corresponds to the original r equals 0. This part here you can think of as corresponding to the original space-time. If you think about the arctangent that we use to change coordinates, corresponds to v going to infinity, and this part corresponds to u equals minus. Okay, and all right, so now we have this picture, and the benefits of all this stuff I said about the conformal transformations and the fact that you can lift things, the conformal transformations respect causality, and the fact that you can lift you know, like this example, you can lift relations and they still remain true. So then you can do things like go in this picture and I can draw a point here and I can draw a point here and I can say, okay, you know, with respect to the sort of Minkowski metric of the blackboard, you know, the future light cone of this, you know, would look like that. And I can see that Q is in the causal future of P, you know, all drawn here. And then that, you know, that has an actual meaning in the original Minkowski space. You know, there's nothing, it's a completely rigorous procedure. Okay. All right, so that's first thing that you can, that's a convenient way to sort of draw things and indicate causal relations. But the importance of this goes beyond that, because we can also talk about now these boundaries. These are convenient both for physical interpretations of things and even to prove things mathematically. All right, so first thing we do is, so this triangle has there's an obvious, so this is an open set in the R2, that's the blackboard, and I can take its closure, right? Right, and then these things have names. So this, well, maybe I'll just redraw over here. All right, so this hypersurface, so this thing here, we call this I plus, which is called a future null infinity. Or maybe, sorry, there's something I wanted to say first. So I'm giving these things these names right now. So again, let's just review what we did. We killed the sphere. We quotient out by the sphere. Then we did this these change of coordinates, and then now I'm talking about the boundaries of these things. But this is all after I've quotiented out the sphere. We'll see that it's also relevant to, you know, not just add a boundary to the thing without the sphere, but to think about what happens when we lift all of, you know, even this. In other words, you might want to think about what this conformal transformation does even to the original metric with the sphere. We'll talk about that in a second, right? Just that sometimes can be a confusing point. All right, so still forgetting about the spheres. So we call this point I plus. This thing, it's called I minus. So this is called past null infinity. This thing is called this is a point here, right, on the blackboard, is called future time-like infinity. And then this this little thing here is called past time-like infinity. Okay. And one thing that you can check, for example, so where, I mean, these names are very suggestive, right? So if you take if you consider any null curve, any, like, let's say, just for concrete levels, like, so take a null geodesic and in Minkowski space, and, you know, send it along this project it all the way to this diagram and draw it. If it's a future oriented one, it will asymptote to this boundary, and if it's a past one, it will asymptote there. That's why this is why this all null geodesics to the future go to future null infinity. Similar here. And if you do, for example, so maybe if it's your first time seeing these, it's useful to draw these familiar curves from Minkowski space. So the, you know, so like this could be a v equals or sorry, that's not v equals constant, u equals constant, sorry. So u equals constant curve in this diagram looks like that. That's maybe less weird. So the more other important things are, so what about t equals constant? So for example, well, let me erase this. So the null curves are easy because that's 45 degrees. What about, like, say t equals 10, t equals 100 in the original space? What do those look like? Those are going to look like, things like this. So these are like t equals constant, right? When they get projected. You can consider this as an exercise to make sure this picture makes sense. And then, oh yeah, so these are t equals constant, right? And then all right, and then finally, it's also, we have r equals constant. So here's r equals 0. I already noted that. But then the other constant are curves, so will look like this. R equals constant. Okay. And so these, for example, are time-like curves. They asymptote to future time-like infinity in the future, and the past, they go to the past time-like infinity. Okay, so that's that. Questions? None. Cool. And none on the Zoom? None. All right. Okay, so now, all right, what's the next point I want to make? All right, the next point I want to make is that, so with these definitions, we can make certain definitions, which will be useful, which are useful to talk about later. So for example, so now using the fact that I have the metric on the blackboard, I can do things like I can take a subset. I can let J lie in this, all, sort of on the blackboard. Of course, I'm sort of saying it in this silly way, but I just mean that this set naturally lies in R2, right? I can let that go in there. Well, maybe not do J, because I'm going to write J inverse. Let W lie in there. So that could be some, this could be W or something. And then I can look at, the causal past of W. I can compute that, what that is. I can use just the Minkowski metric on the blackboard. And that's consistent because they're all conformally the same. It's consistent with the original metric. So, I can look at the past things that can go to the past of W, whatever that may be. All right, so this is now a very useful thing. So because of this sort of boundary we've added infinity, I can talk about the things that are in the past of elements of infinity in some way. That's not something that I could easily do, with the original form of Minkowski space, right? And that's very important for defining, for example, we'll see in a bit not that we won't go into it in that much detail, but for defining properly what a black hole is, for example, uses the fact that you can do that. All right. Okay, so now, next thing that I want to note is, so now let's discuss quickly. So let's discuss now putting, so we can extend, well, I don't want to say. So we had this relation here. Okay, and so, well, so we had this, other way to think about it is this was our original metric, M. Then let's call, now I had unfortunate notation because I think I already used M tilde for the quotient, which is maybe unfortunate. All right, I'm going to call this du tilde dv tilde. I should have reserved M tilde for it, but let's call it M check because it's already M tilde. So now what I wanted, so this was the original metric. And so this whole process, what it's done is that I've found this metric M check, which is defined on this finite, on a bounded domain of subset. I've written this one as it's equal to to a conformal change applied to the original metric. And I've done this, and this transformation produces something which is of course regular. Now wait, okay, but this, oh, sorry. I guess in my notation, I should write, this is m tilde. So this is from the quotient, just the du dv, there's no sphere here. I multiplied by this thing, and I've gotten this, again, the Minkowski metric here. Now what you can ask is, well, does this make sense with the, if I put back the sphere in? And it does, and that's a nice point. So now let's go back to this original m. So remember, this m is dt dr squared plus r squared. Well, now let's maybe write, well, actually, let's leave this. Okay, so this I can write still in the du dv, and if you work what r is, so r is 1/2 v minus u, right? So this becomes plus 1/4 v minus u squared. Okay, and now you can, so these you can write. So now I can do the u tilde and v tilde change of variables. I could do that here still to define a new u tilde and v tilde, and I can look at what I get when so in u tilde, v tilde, and now let's keep the whole sphere around. I do the same coordinate change on these ones, and I can multiply by the same conformal factor. So now let's all right, and I can try to see what I get, and it's not just a little exercise in some trig identities. That what you end up with is all right. So what we already know, that when I multiply by this here, I'm going to get du tilde dv tilde. That part doesn't change. All right, and then on the other part, what you end up with is this. So sine squared, again, if I did the trigonometry correctly, get this, and then you still have this metric on your S2. Okay? All right, so you can exercise. All right, and now with this form, we can go back to this picture, which let me just redraw it. All right, and I can try to, think about what do these, so before, and still in just the two-dimensional sort of setting without the sphere, this piece I added in is just like a line segment that made sense in the Minkowski space of the blackboard. So now the question is, what goes on if I put in the sphere everywhere? And well, I mean, the only thing, the problem that can occur is, of course, that this factor, doesn't make sense. So, this doesn't blow up anywhere. The issue is that this might be 0 some places, right? And that's not, in this particular case, is not difficult to see. So what you see, first of all, so this I plus, you can see, so maybe I should have made this more clear, that this I plus here, well, I just drew this line here. This I plus, corresponds to, so V, it's this boundary, V equals pi over 2. But the U does not, sorry. The U does not include those. I mean, this is implicit in how I was talking about it, but right, this endpoint is not included in I plus, right? It's an open, it's V equals, okay. All right, and that's now that when we go up to this question, that's quite important. So I can go to V equals pi over 2, and then, so this sine squared at pi over 2 minus u will be okay as long as u stays away from minus pi over 2 or pi over 2. In other words, this factor won't vanish. And so, this conformal metric extends to this I plus also with the S2. So this is why we. So I can do this compactification of that conformal transformation with, I can add a cylinder at that point, right? I minus is the same. Right. And then, but now these ones, it's different because say this point, this is a space like infinity, whatever they call it. Let me just write. So let's look at the space like infinity. That thing there in the picture. So there, that corresponds to v equals pi over 2, and u equals minus pi over 2, where of course this factor vanishes, right? But if you think about it, it sort of vanishes, well, yeah, how do I want to say it? It vanishes in the same way that when you do sort of polar coordinates in R2, how the R squared, d theta is vanishing, as you go to R equals 0. Right, so exercise makes sense of what I'm saying. It vanishes in a similar way, and so you can implement a coordinate change so that it's reasonable to think of that this is a point, right? This is really a point in the compactification, and it's similar. These ones and these ones also. Again, you can check when you plug in the right values of v, the pi over 2s, plus or minus pi over 2s everywhere. These ones and these ones, this factor will also vanish. And that's telling you, what that's telling you is that these are really, they don't become spheres. They're really points. So, yeah. So I'll just say these are points. I'm not going to say more about this because it actually will play essentially no role in anything I talk about, of course. What's really this I plus is what's important. Okay, so that's that. All right, so that's the this compactification of Minkowski space, which plays a very important role as a model for other constructions we'll do. So again, it's a good place to stop and ask, are there questions? Yeah. Sorry? Oh, here, yes. That's what you meant? Yeah, thank you, sorry. Other questions, comments? No, okay. So now, all right, so soon we're coming upon our mid-class break, which we're all excited for. But before we do that, I want to discuss a way to sort of interpret, think physically about what should you think of these, like say, future null infinity as corresponding to. So the idea is, all right, so let's suppose, we are observing an isolated sort of, event, an isolated event very far away from us. Far away from us in Minkowski space. Okay, so sort of what happens? Let's draw this in this picture. All right, so here's this. All right. So okay, so let's suppose, so here's some, let's say this is t equals 0. Okay, so suppose something happens. I don't know, there's some, there's an event that happens here. Okay? And we're imagining like we're doing astrophysics, we're watching this, we're really, really far away. So you might think, I don't know, we're like way out here or something, right? We're far away. So there's us. All right. And now we're interested in eventually in sort of seeing this thing. So now, of course, I mean, if you wanted to, look at this in a remotely serious fashion, you should say what this thing is, et cetera, et cetera. But we're being very, this is very a first pass, these ideas. So what we know is, okay, I mean, well, if this is, say, something which produces light, it should move on null curves. And so kind of the information stuff is coming out like this way. Let's say they're photons coming out that way. We're way over here. We're sort of far away. And so, okay, we're not going to see anything. And then remember, I drew these pictures of a constant R, the kind of arc, right, in the diagram. So if we're just sitting, not doing anything, we're going to come, and the first time we'll sort of, we'll see things are kind of here, right? And so what you see from this picture is that sort of and it's natural to consider the limiting situation where we are sort of infinitely far away. So kind of in the limit, as we go infinitely far from the event, then we will see the event sort of on future null infinity. So this is why. So you often you model a faraway observer of an isolated event like black holes merging or something. You think that people will often say like, we are on future null infinity, seeing whatever happened. There are many ways you can think about it. This is some maybe a more pedestrian way of thinking about it, but basically this. So from the event, so in the limit, as we go infinitely far away from the event, we sort of, the observation, occurs, observation happens on future null infinity, right? And so future null infinity is sort of, important, like, because we are there, and we'll see that somehow the weak cosmic censorship's conjecture, or let's see, it's first very informal version, is that kind of, I plus always exists. So in a way that we kind of, there's nothing bad that happens. So all sorts of, all sorts of strange and singular things can happen in general in relativity. But if you're really far away in the limit, and you're sort of far away enough that you live on future null infinity, you're always fine, and nothing bad happens. Okay. Yes. So maybe actually that's a natural place to do our 10-minute break. So let's take a break here. Let's reconvene in 10 minutes at 4:02. So so this first part of the lecture, we sort of said what I want to say about Minkowski space, but now, of course, I mean, eventually we want to study solutions to the Einstein equations, non-trivial ones that are not Minkowski space. So the question is, we want some version of, to what extent can these types of constructions be used in more general settings? All right, we'll see in certain senses that they can be used in a lot of generality, and certain aspects of this diagram do not easily generalize fully. Anyway, one step at a time. All right, the first natural place to start is with a 1 + 1 dimensional spacetime. So first thing we can consider is the following. So here's our proposition. So let mg be a 1 + 1 dimensional Lorentzian manifold. Right, and pick some point P and M, then there exists some open U with P such that and in coordinates well, there exists an open U and P. There exist coordinates UV covering U and a function omega from this set to the positive reals such that G restricted to U equals minus omega squared du. Okay, so that tells you that, so this, this is a sort of similar to this first step, this, where we got this dt du squared, and I just introduced, just by hand, we just wrote v and u, t plus r and t minus r. So that might seem ad hoc. So that part, if you work locally near a point in a 1+1 dimensional space-time, is not actually ad hoc. Well, I mean, you have to allow for this conformal factor maybe, but you can always pick, this actually, you can always write the metric like this, right? If you want this as a form of some kind of uniformization theorem in the Lorentzian setting. Okay, and so why is this true? So uniformization in that this is like all 1+1 Lorentzian metrics are locally conformally flat. Why is this true? Well, it's sort of kind of clear. So what's the point? Well, so at any so for any, if you pick any q in your manifold and look at the tangent space there, you can always write this as a span of, let's say C in and C out, where these are two null vectors, right? This is where these are null, right? And okay, and in principle, at any given, point, it's, oh wait, I'm hitting this aforementioned boundary. Okay, so you can always write it as a span of these two null directions, right? This is just 1+1 Lorentzian linear algebra, right? So one thing is there's no way, so remember null, right, means that the norm of these is zero. Okay, so there's, of course, as we discussed in the first lecture, one of the annoying things in Lorentzian geometry is that when you have a null vector, there's no canonical way to normalize it. So I can't, so I don't, but, that's fine. And all right, so then so we have this, and then basically it's kind of clear what you want to do. So the first thing is, if you want, this is an exercise. So for suitable, so let's, okay, we have these are vectors. So let's call, I don't know what's the notation I want to use. L out. Let's call that the span of this, and L and right. So you can write the tangent space at any point is written as, you can think of it as the direct sum of these two directions. Now, what I claim, exercise, if you work close to a point, so for suitable u, you can make a consistent, you can do a labeling of the Ln and L out in a continuous fashion. Right, this, all right, in the exercise, make sure you understand what that means. do it. But right, this is all I'm saying is I can, you know, if I do this, these ones I call out, these ones I call in, right? And it's continuous. Okay, so first of all, I can do that locally. And then what are my coordinates just going to be? The coordinates are just going to be, I'm just going to, I can look at, so I can, let's pick, here's my point P. I can take the, I can define, so I have, say that a null, I can look at a null geodesic in the L out direction. All right. So this is going to be a bit of a proof by picture. Oh, now I'm hitting this. Wait, all right. Let me move to the other board. All right, so I'm at my point P here. So I can define, let's call this gamma out. I can define gamma out is the null geodesic. So let's say is a null geodesic, right? Because again, there's no canonical way to decide on the size of the tangent vector. So I just pick a null geodesic in that direction of that line. A null geodesic with gamma dot at 0 parallel to L out. Right. Similarly, I can do some, you know, I can define a gamma in, right? All right. Again, these, I'm working in a small enough, so I'm not worried about geodesic equation not being solvable because I work in a small, this is all local, so there's no issue there. All right, and then, and now I can also, these things, I can introduce some affine parameter along them. So we can introduce, you know, let's give a label to the affine parameter. So for, so let's let V be the affine parameter of gamma out. That by affine parameter, I just mean, you know, it's time function that it solves the geodesic equation with. And then similarly, let U do the same thing for gamma in. I can also do that in such a way that, for example, like I can make sure that V at P equals U at P equals 0. Okay, so now, so this gives me, so what that means that along this thing, I can talk about V equals 1, V equals 2, et cetera, and that gives me different, you know, places on gamma out, and different values of U give me different places on gamma in, right? And now I kind of, maybe you can already guess what's going to happen. Now for each, so now let's let, all right, so these will exist, you know, in some interval. I could, right, if I pick for a suitably small, for small enough interval. Right, small enough interval I. Okay, and now, then for each V in I can define, so I'll define it like this, gamma in comma V to be a null geodesic starting at gamma out of V and parallel to L in. So remember, at every point, I have a direction, outgoing and ingoing direction, and it's all consistent, right? Because it's all in a small neighborhood. All right, so this just means, so for each of these, so this is some V, I this is gamma in sub v. Right? So I can call these ones, I'm just going to call these gamma out 0, and this one to be consistent, I'll call comma 0. Right? Because this is the one which comes out of 0. This one comes out of v. Right? Now, hopefully you can imagine where this is going. Right? And now I can do the same thing from this ingoing one. So similarly, for each u in I, we define, we let gamma out u be a null geodesic starting at gamma in, well, which is the same as gamma in comma 0 at u, all right, and parallel to LL. Right? And well, it's a bit of a proof by picture, right? So then you have your key here, you have this direction, and now, so proof by picture, this is a coordinate system. But okay, I mean, that's something that you can, once you sort of have the right setup, that's not difficult to prove. So exercise exercise. So now the affine parameters along all of these, let me finish telling you what the coordinate system is, and then I'll say exercise is coordinate system. All right, so now, okay, well here's, so claim. All right, so again, if I do it sufficiently, this picture is impossible to read. If I make some sufficiently tight neighborhood around P, then every, so if you, so suitable open U containing P, then what do I say? So Q in U lies at the unique intersection, lies uniquely at a intersection of one of these gamma out U and a gamma in V, right? So in other words, you have all these lines going in, all these lines going out, and every point lies on some intersection uniquely, right? And then so using this, so we can introduce, so then this gives the UVs, we can use these UVs as a coordinate, gives UV coordinates, right? And then, so you should check that. And if you believe that, then it has to be the case that the metric looks like that. Why? Because the d by d, if you think about the, I claim then that these have to be 0. Because what are these? Well, these are coordinate derivatives, but because of how they're defined, so d by dv means you hold u fixed, right? And you move v. But holding u, say, fixed means that you stay on one of these lines going out here by construction, right? And then moving v. So it has to correspond to a derivative in that direction. But this whole direction is null by, that's how we started the whole thing, by splitting the L out in the end. So therefore, the thing has to be 0, right? Okay, so the upshot, so du is 0, v is 0. So it's this nice thing about 1 plus 1 dimensions. There's nothing like left over. All you can have, therefore, is that it looks like this. Well, I guess it could have a, you know, I can switch the sign of it. Yeah. Anyway, so that's the all right. So that's nice. So that means what? I guess I should. Questions? Make sense? Right. So that means that this Penrose diagram kind of stuff works very well, at least locally on 1 plus 1 dimensional spacetimes. All right, and why is that? That's because now, so once you have the metric in this form, the other parts of the construction I did on Minkowski space are, manifestly are general. So the final parts where you just have to pick. So these are U and V just in some, set. And I said, now you just pick any diffeomorphism you want, from R to a bounded. So, okay, it could be that these already cover, a bounded set. But you can always do a diffeomorphism to make the range of U and V a bounded interval at the expense of just changing the conformal factor, right? So therefore you can do all that. Okay, of course, in reality, we don't always want to work locally. I mean, working locally is a good place to start, I guess. But you don't want to be restricted to that. So here's a little proposition that I won't prove, but it's a nice exercise. All right, so suppose MJ is globally hyperbolic. So here we're the self-contained aspect of the lecture breaks down a bit because I introduced this before. But all right, suppose this is hyperbolic, 1 plus 1 globally hyperbolic, 1 plus 1 dimensional, and simply connect it. Then you can do this globally. Right? Okay, that actually won't really play much of a role in anything, but I thought there are some settings where you can make this global. Okay, but anyway, we're forgetting this local global thing, whatever. I mean, a more serious issue is that we want to study, we want to study, 4 space-time dimensions, right? Okay, we can still sort of try to get up there slowly. So as a first step, you can, we have this Minkowski space example, and how did we get to the 1 plus 1 dimensional thing? We did that because it was spherically symmetric and we could quotient out by something. So that's a very natural setting where we don't have to work very hard, and we can just use this stuff we did in 1 plus 1 dimension. So, all right, so we want to move towards 3 plus 1 dimensions. All right, so as a first thing we note is, okay, we could work with spherically symmetric spacetimes. Right? Like Minkowski space, or not really IE, I guess, e.g. Minkowski space. All right, so in this setting, I mean, I'll spare you a formal definition of spherically symmetric. Let's just say, well, I know. We'll just get it, fine. Let's just give something. I won't give all of the formal assumptions, but okay. So this means that you have an action of SO3. You want these you want space-like orbits in general. So your sphere should be space-like. You can have fixed points. Like so on Minkowski space, we have fixed points, right? There's r equals 0. So we want to allow that. Can have, but the fixed points, if they exist, should form a smooth, say, time-like curve. Time-like curve, right? Then in this setting, you can, you can sort of then, so like in Minkowski, oh, I said, yeah, S3 space-like orbits, and I left out the most important thing, and acts by isometries. All right, so you can consider a space-time like that. All right, and then just like in Minkowski space, you can quotient out by the SO3. So you can, in this setting, you can quotient out the SO3 action to get again, so that'll kill two coordinates. So you'll get something 1 + 1 dimensional to get a 1 + 1 dimensional spacetime. Of course, what's annoying, this might have boundary. So maybe with boundary, that's because of the fixed points, right? Like in Minkowski space, you have that r equals 0. So that's a little annoying, but that's just, you have to deal with that. All right, so you get that, and then you can, basically argue as we did, and then argue as in the as in the regular 1 + 1 setting. In the regular 1 + 1 setting, to sort of carry out these Penrose diagram constructions again. So that is to say, you can quotient out by the SO3. In general, you can always do this picture sort of locally using this proposition. And then, okay, some settings you might hope that you can globally do. So in Minkowski space, of course, there's the r equals 0, which is like this weird place we have to avoid. But outside of r equals 0, we have this nice UV coordinate system that covers everything, right? So you can carry out Penrose diagram like construction. Okay. However, that's great. And well, in fact, you could stick with spherical symmetry and do lots of interesting stuff. But ultimately, we don't want to just do spherical symmetry. We also want to consider general spacetimes. And okay, so, and now here we have to kind of up the complexity a little bit. But I will now explain. All right, so what about the general 3 + 1 dimensional picture? Okay, so yeah, well, here in general, it's sort of it's a bit complicated. I guess there are probably various ways to make sense of Penrose diagram-like constructions in the setting. I'm going to give one way to do that, which uses what's called a double null, the double null foliations or the double null gauge. Right, so the way that we'll make sense of this is we're going to use the double null gauge, right, which will also play a role later in the course when we study things like the characteristic initial value problem. Okay, but we're going to start start sort of slowly build up to that. Okay, so let's let mg just be a 3+1 dimensional Lorentzian spacetime. Okay, and as a starting point for our construction, so before in the 1+1 dimensional case, I just picked a point, and then I looked at these outgoing things and these ingoing ones, and then I sort of crossed everything and used that. So now I'm going to instead start with a sphere, right? So now let's pick, you know, an orientable, say, so let's say topological sphere. And so that's 2-dimensional. Also want this to be space-like. It's actually, well, and what I'm about to say, it's actually not important that it's a sphere. But in the in almost everything that we consider in the course, probably everything, we will be interested in the setting in which they are spheres, right? Okay, so of course I can't. Well, now we have issues of drawing pictures. So so imagine this is my sphere. Of course, that looks like an S1, but let's imagine it's a sphere. All right, and now what I want to do is along the sphere, I'm going to do the analog of, you know, so here I picked the outgoing direction to ingoing direction. But my starting point was just, I started with a point there. You know, that's where everything, and there I just call this one out, call this one in, and, you know, that was fine. Here I have a whole sphere. So along the sphere, I want to do the same thing. So I want to pick you know, an outgoing 2 null vector fields. I'll call, well, maybe instead of out and in, I'll call them L and L bar. That's a little shorter. All right, I'm going to I'll draw the picture and then I'll say. So at every point on the sphere, I want to pick 2 null vector fields. So for every P in S2, I want to choose L and L bar, which are null and normal, which are normal to the S2. That means so they have a 0, they're orthogonal to every vector in the tangent space S2. And I don't want these ones, you know, these should be different. So make sure that their inner product should not be 0, so that they're different, right? Okay, and then there's you might wonder, oh, can I always do that? You know, it's some orientability issue. You know, exercise, think about it. In practice, it's actually the way these things have, at least in the say last 15 years of using these things, those particular questions are not that important. But it's a nice little. You can think about whether there are actually topological obstructions to consistently picking this pair of an S2 in a 4-dimensional manifold. And I might even know the answer or not. Anyway, but okay, let's assume you can do that. All right, and now the basic idea is, I did this 1+1 dimensional case because it's visually, you know, it's a little more intuitive, but basically we're gonna do the same thing. So the idea is now, all right, so you have this, it's hard to draw, but you have this sphere, you have 2 choices of like an in and an out. And so first thing I'm gonna do is follow all of the outgoing directions on the sphere. And that's gonna create all these null geodesics, take the union of all of them together, and that will create a hypersurface, because now there's a whole sphere of them. But you have a sort of a hypersurface ruled by these null geodesics going out, right? And then I'm gonna do all the other ones. That's gonna give me sort of in the same way that I had the other direction. But now these are not curves, these are hypersurfaces. And then I'm gonna have a set of hypersurfaces going in. And then I'm going to, just like I did there, I'm gonna try to do that, you know, all over the space-time and try to have these things intersect. Now it won't be points anymore. I want them to intersect in unique spheres. Right? But that's, you know, it gets hard to draw, but that's the idea. So let's, I guess, go over here. All right, so yeah, so how do I want to say this? All right, so it's to each, so for each P in my starting sphere, let's go ahead and call this sphere. So in the same way that I ended up, each point in the 1+1 dimensional case had a u and v corresponding to, where these, on what curves it lied on the intersection of. Every sphere here is going to lie on, have two numbers associated to it. So let's go ahead and this one's, we're going to normalize this one's 0, 0. So for every p in this sphere, which is 0, 0, 1, yeah, for every p in there, I'm going to have, say, gamma p out be the null geodesic starting at P and parallel to L. Right? So that's these L's everywhere, right? And then the union of these. Right? So these are a bunch of null curves on each coming out from each point of the sphere. I take the union of those. The union of these is a hypersurface, is a three-dimensional hypersurface. Three-dimensional hypersurface, which we'll call H0. Right? And that's the analog of the first outgoing one. Again, it's hard to draw, but well, I don't even know if it's a point in drawing. I mean, it's like all these, these guys all coming out, sort of. And then similarly, for each p, define gamma p in to be the a null geodesic starting at P and parallel to L bar, right? The other direction, right? And then the union of these gives a three-dimensional hypersurface. Remember, and we're always, I don't always keep repeating it, but we're always constantly using that we're working locally near a point so that we can, we're not worried, null geodesic, we can always solve all of the null geodesic equations we want. The S is compact, right? So there's no, no issue. Union of these gives some hypersurface, gives again a 3D hypersurface, which we'll call H bar 0. Maybe questions? Gotten very few questions. It's a little disturbing. All right. Next, again, we're just mimicking the steps here. So the first step, this is the analog of that first step where I drew the gamma out and the gamma in. Then the next thing I did was I introduced the affine parameter along both those null geodesics. That's like starting, my V and my U. I'm going to do the same thing here, except now instead of, it's not going to be, because now there's spheres everywhere, what I'm going to do is I'm going to, these are 3D hypersurfaces coming, starting from the sphere, and I'm solving these null geodesics. Now what I'm going to do is I'm going to foliate those hypersurfaces by spheres instead of, that's sort of foliating them by points. Now I'm foliating by spheres because there's spheres everywhere. Right? So, all right, so now, well, okay, so first of all, I can extend L, so this vector field L and L bar, these are first defined just on S2. I can extend them to S2 to H naught just via just taking it to be the geodesic via the geodesic equation. I just take L to be the derivative, the tangent vector to the geodesics, which are defining it. And similarly, L bar. Okay. And then using one, now I have these. Yeah, it'd be really better if I maybe here some slides would be useful with some 3D pictures. But so now I can use these vector fields to sort of push forward the sphere along. I have this, again, this outgoing, all these lines coming out of the sphere in one direction, and I want to just push forward the sphere by this vector field, and that will give me a full foliation. All right, so flowing by L and L bar, i.e. following the geodesics, yields foliations. We'll call it S. Well, how do I want to say it? So S. So this one is, say U equals 0. So let's call it SU tau. So this is a foliation S0 tau of H0. So this, again, so you have, here's your sphere. These H0s they're all these null geodesics coming out of this, and then I'm just getting all these spheres that foliate them, right? I get that, and then similarly I have, well, S, say tau 0 of H bar 0, right? And then on the other one, I do the same thing. Okay, now, again, difficulties of drawing, sort of ignoring those difficulties. Again, we're now going to proceed to this same step. So remember, so what happened? So we started with, we have this with these two lines, then we sort of labeled the curves with some function, and then I drew null geodesics going the other way, right? And then I did that everywhere, and you eventually get this grid thing, and every point lies on a unique one here. I do the same thing here, except, now at each step, each point I have a sphere. And so I'm going to redo, basically, I redo the initial construction I did now on each of these spheres in the other direction. So now, so for example, so for each, all right, so we have this sphere here. Okay, now first of all, so this sphere is a foliation. These spheres are foliating this H0. This comes out of that first sphere, right? You have all these spheres. So we already have the vector field L, because that's the one coming from the geodesics, which define those. But then I can pick, so for each of these ones, I can, we can choose L bar. I can pick a null vector in the other way, which is, say, null, and satisfies, I mean, you could do various things, but let's just, here I can pick some normalization, say -2, all right? So I pick a vector going in the other direction, right? All right, and then you can define, and then in from here, and now, okay, and then for each, P and S0 tau, I can look at the, the ingoing. Oh, this is too low. Keep it going. Sorry. Go ahead. All right, so for each, all right, so for each P in each of those spheres, I can look at the collection, I can look at the null geodesic parallel to this other null vector. So this is going the opposite way of the hypersurface it's on. All right, and the union of all of these gives another null hypersurface. The union of these defines, call it C bar tau. Right? So again, it's really the analog of that picture, except there's spheres everywhere. And so I can't really draw it. But you know, it's just, I mean, you can imagine, I mean, ultimately it's like you, I mean, even in maybe one other, in Minkowski, you can imagine this picture, right? You have these spheres, right? Everywhere you can draw. And then, you know, you can also, you have spheres, these cones going down like this, say. I don't know if this picture is useful at all. Anyway, somehow you can imagine, so stay away from this, where all these cones are starting. That's not a, stay away from that point. So look over here. Now imagine, you know, it's this, it's the analog of, I mean, the more I draw, the worse it gets, right? But I mean, you can imagine, right, all these, you see how all these different hypersurfaces will intersect at unique spheres. And every point, okay, forget about this axis. Every point away from there lies on a unique sphere, you know, and does lie on a sphere. All right, so that's all we're doing this here, except I'm not, when it's easy, when you draw the picture of Minkowski, somehow it's natural to start at, you know, at this r equals 0 sort of and do it like that. In reality, what we're doing is starting at a sphere here, and I'm just sort of doing that, you know, starting in this, well, the sphere is sort of this whole thing, and I'm drawing these ones everywhere and drawing these ones. That's all. That's all that's going on. All right, and let me get to the punchline before we end the lecture. All right, so we do that, and then okay, so it's, okay, now it's starting to all get tired of this. So similarly, you know, you define C tau. So right, so on this, you have this original outgoing one. Then each of the spheres on that, you send in ingoing ones. Then on the original ingoing one, each of the spheres there, you send outgoing ones. Okay, and this allows us, you know, so finally, all right, we have the following. We obtain the following fact. All right, so all right, so if you let, you know, so there exists, you know, open U containing our original sphere that we started with, so that such that U is, you know, is foliated by these spheres S2 UV, and this S2 UV is just what you get on the intersection of this CU with, or wait, with, maybe I want to write it like this, CV. All right, so these two things all intersect, you know, okay, then they're all the exercise, you know, you have to check that they actually all intersect transversely at its spheres and every point lies on one, et cetera, et cetera. But you could do that. All right, so that's that. And this is kind of where in the 1+1 dimensional case you sort of stopped, right? Because then there were no other coordinates. So we determined that everything lied on a, every point had a UV associated to it, and that was our coordinate system. And then in the 1+1 case, by the way they were defined, you know, the coordinate derivatives d by du and d by dv had to be null. So we got this simple form of the metric. In this case, you know, it's a little annoying is that we're not done, even after all that tedium. You know, we still, we need coordinates on these spheres, right? In principle. Okay, but there, you can do that. And so what's the way to do that? Well, we have some choices actually, but I'll just describe it quickly. So, well, what you can do is first of all, I mean, you could start, just on a general sphere, there's no, there's not some general prescription for picking your, I mean, there are different local coordinates you can do. So we start with, some coordinates, on sort of the first sphere. Okay? Whatever you want. Polar, I mean, depends on what problem you want to do, or you can just keep it abstract. So let's call these, I'll call them theta A. So you should think A is going 1 and 2, say, right? And now we want to, and these will, of course, in general, are defined on a subset of S2, right? You cannot, there's no global coordinate chart on S2, clearly, because it's S2. Okay, and then, well, what you do basically is you want to extend these to, so let's say on, on some subset, these are defined on some coordinate chart, right? And now, basically, your choice is the following. So now what we want to do is we want to sort of just, flow them by our vector field. So every sphere lies at the intersection of, some outgoing null hypersurface and some ingoing null hypersurface. So the natural thing to do is, just, move out as far as you need, transport these out by L as far as you want, and then move them in. So you can, so that's what we'll do. So the first thing you can do is you can, you can flow by following the curves, the geodesics, the outgoing geodesics. So by flowing by L, you can extend, you can identify, you can extend W, to subsets, of the spheres on the outgoing foliation. Right, so you have all these, you have this cone going out, have all these spheres, you pick some subset of the first sphere, you can just, flow by the null geodesics, I define some subset of all the other spheres, and then you can extend sigma A to W there by just declaring that, L of sigma A is 0. So again, you should think in the spherically symmetric case where eventually L is maybe would be like d by dv of something. Of course, like d by dv of a spherical coordinate should be 0, right? Because this, yeah. So you do that first. All right, so that defines it on all of these outgoing ones. And then okay, and then having, so now you've defined, so now these, all right, and by doing different, by having a full set of local coordinates on your original sphere, this defines a full set of local coordinates on all of the spheres on this first outgoing cone. And then having done that, you then, then you can extend these coordinates to the rest of you by basically now by declaring that this one should be 0. Right? So you flow them out to label all the spheres, get coordinates on all your spheres going out, and then you flow them in, and that by this first claim that U is foliated by, every point in U is on some sphere at the intersection of some of these. This, now defines coordinates on all those, uniquely on all those spheres, right? And so what's the upshot? So the upshot is a coordinate system in U of the following form. Different normalizations here, but all right, so we'll put -2 omega squared du dv. So that part is familiar from the 1 + 1 case. All right, but now we have all these they're all these S2s, right? It's not spherically symmetric, right? So there's some metric there. So we'll have put some metric AB here. This. All right, well, I'll say a bit about it, but again, a lot of these are really things that if you want to actually understand, there's no shortcut through playing around with it yourself and suffering a bit. All right, so let's look at the pieces here. So you should think the A and the B indices correspond to tensors on S2, to tensors on these spheres that lie at the intersection of these cones. All right, so now let's just slowly, the last 5 minutes, just unpack what's going on here. All right. All right, so for each, so again, this part is familiar. So then now for each U and V, so if you fix U and V, then that defines a sphere, right? Which, like you can think that picture if it helps you visualize. So if you pick one of these cones and one of these cones, there's some sphere where they intersect. On that sphere, we have local coordinates that from the local coordinates on the original sphere, I promoted them to the whole spacetime by transporting this way and this way. And this is just the induced metric on that sphere relative to those coordinates. All right, this is the standard notation of, you often use slash quantities to denote objects which are defined along some sphere in a foliation. All right, so that's fine. That's from when the d theta, this G/AB, d theta A, d theta B is from there. Then there's this extra term, which is this thing that's quite annoying in general, is that, well, it's not the case that, oh, did I not? No, I did define. Yeah, it's not the case. So these U and V are these functions, right? The level sets of U and V, by definition, like U equals constant or V equals constant, are going to determine one of these cones, right? So you might, if you've never thought about these things before, only thought about spherical symmetry, you might have hoped that d by du and d by dv would end up being null vectors. Those coordinate derivatives would be null vectors. But it doesn't quite work that way. And it has to do with there are all sorts of ways that you can think about it. But one way is if you just think about how these theta, these things were defined. So, what you would kind of hope for is that you have this piece, and then there's just no cross terms between the UV and the theta. But it just doesn't, you kind of can't quite get it to work because you have to pick an order of how you move the thetas around. So first, in this case, we did the L. We pushed the theta coordinates out by L, and then we did L bar. So it's certainly the case that, at their final resting place, all these theta functions, these coordinate functions, L bar is always 0 originally. This is always true because that's the last thing we did. And so that means that that's related to why there's no du d theta term here. But somehow, because you did this at the end, and because outside of spherical symmetry, there's no reason why L and L bar should commute. You sort of lose this L, that L of the theta things was 0, you have that initially. But then once you move them in, because these things don't commute, you don't necessarily have that. So in general, you pick up, this thing. And this is, well, it's quite annoying sometimes, but that's just life. All right, that's called the shift vector. So this is a thing called the null lapse, which E slash is just the induced metric. And this is the shift. All right, so okay, so I'm about out of time, but so what we'll see next time is we can still, so even though we have this shift, it's not spherically symmetric, we can still use this foliation still, even just looking at the UV part of this, still contains a lot of useful information about the causal structure. It still is the case that constant U and constant V are null hypersurfaces that, again, at least at this point locally, certainly are telling us, we can read off various causal properties just from subsets of U and V. And so you can still consider the quotient where you dump this thing, rescale these to be compact, and you can still draw that set, and you can still capture some of the kind of useful properties that we had from the other Penrose diagrams. But I'll get into that next time, and maybe in the last minute, just if there are any questions. But there haven't been any questions. So why would I expect any now? Yeah, because it's so clear. All right, so I'll see everyone on Wednesday for this, and on Tuesday. Tomorrow there'll be, who's at 10? You know? Yeah, so John will again open at 10 tomorrow. All right, so thanks, everybody. See you.